storms just forced more than 6,000 Airbus aircraft into emergency updates, one of the largest aviation recalls ever. And the trigger wasn't mechanical failure. It was radiation from space corrupting a flight control computer. I'm Dr. Amanda Fetch, aka Dr. Amanda Analytics, Space Situational Awareness and AI researcher. Since November, I've been leading chatter discussions on the Chatter audio app, social audio I should say, on rising solar storm risks, outages, and radiation events affecting aviation, satellites, and power grids. Today, in this video, I'm going to break down what happened, why it matters, and how AI-driven clustering, including the use case for, again, DBSCAN clustering that I presented at the International Space University AI for Space Applications workshop, how this use case could basically be applied to DBSCAN clustering, and how this could potentially help us providing early warning before events like this happen again. So according to BBC, on October 30th, the JetBlue A320 flying from Cancun, Mexico to Newark, New Jersey abruptly dropped altitude. People were injured, the flight diverted, and 15 passengers were hospitalized. Investigators discovered the cause, which was a single event upset or bit flip. A high-energy particle, likely a cosmic ray, struck a flight control computer, flipping a single bit inside the ELAC system that controls the aircraft's elevators and roll. That tiny particle triggered a large sudden altitude deviation. This led to an emergency grounding across A319, A320, and A321 aircraft. More than 6,000 jets needed immediate software updates, and nearly 900 required new hardware to prevent future radiation-induced failures. Right now, we're approaching the peak of solar cycle 25. With that being said, there's more frequent flares, large sunspot regions, and energetic solar particles interacting with Earth's magnetic field. Even if a major solar storm doesn't hit us directly, a more active sun overall raises that radiation environment, especially at cruising altitude. So to show you what the sun is doing now currently, here's a quick real-world data snapshot. So when I checked the NOAA GOES X-ray flux chart, which you can basically navigate to the NOAA website, I'll go ahead and add it down to the description within this video. The latest flare peaked at C5.4 at 2038 UTC, which is about 3:38 p.m. Eastern Standard Time, which is where I'm sitting. Right now, the sun is hovering around C1.9. If you're not familiar with flare classes, here's the simple breakdown. A and B flares are usually considered very small. C flares, which are these, are pretty moderate. M flares are considered a bit stronger. Possibly there could be some radio blackouts. X flares are extreme. That's when you could see potentially grid impacts. And so the number after the letter also tells you how strong it is within that category. So for example, that C5.4 is a mid-strength flare. Not necessarily dangerous by itself, but it's strong enough to raise the radiation background at flight altitudes. A C1.9 is weaker, but it's still part of an active pattern. And so over the past 3 days, we've seen multiple C-class flares, including a clear spike on December 1st. That shows we're in an active phase, even without an M-class or X-class event. And so if you want to check this out yourself, as I mentioned at the beginning, you can go to the NOAA Space Weather Prediction Center and click GOES X-ray flux. So the blue 1 to 8 angstrom line is the curve used to classify flares. It's one of the quickest ways to see if the aviation, satellites, or the grid may be under extra space weather stress. And so at that International Space University AI for Space Applications workshop, I mentioned that use case, and what it was built on was DBSCAN clustering that directly connects to what we're seeing now. And so basically solar flare and coronal mass ejection pattern clustering, AI-driven early warnings was what I presented. And the idea is that we can use GOES X-ray flux, SDO solar imagery, SOHO coronal mass measurements to identify precursor patterns that tend to occur before these high-impact CMEs. And so by clustering flares by intensity, duration, and/or magnetic complexity, we can potentially build a model that exposes hidden patterns that us humans might miss, especially those very subtle changes in solar behavior that happen before a major radiation event. And so that kind of AI-assisted early warning could help aviation, satellite operators, and power grid managers understand when we're entering a higher risk window long before the disruptive effects reach us down on Earth. And so what's interesting is that October 30th wasn't a big solar storm day. So why was there this bit flip? Because probably those cosmic rays don't only come from the sun, galactic cosmic rays from supernova and black holes constantly bombard us on Earth. And so even that moderate solar activity can raise neutron flux just enough to increase the odds of a bit flip. And so aircraft fly exactly in that altitude zone where that radiation is strongest. So it's almost like a perfect storm, literally. And so this is why early warning models need to track those subtle changes, not just major storms. And so as microchips shrink, they become easier to flip with less energy. And so what that means for us is aircraft, spacecraft, GPS systems, medical devices, cars, or even ground-level electronics become increasingly vulnerable to these radiation-induced data corruptions. And so what it boils down to is space weather is no longer just a space problem. Now it's becoming a critical infrastructure problem. So in closing, if you found this video interesting, subscribe for more space weather, AI clustering, space situational awareness dives, and to keep you posted, I'm looking to post new analyses every week. So I'm going to leave you with a discussion question. Do you think aviation should adopt a space weather early warning system, just like we use turbulence alerts today? Why or why not? Drop your thoughts in the comments. I'd love to hear what you think. Thank you for tuning in.